So I mentioned in the video for question 3 about this number, Avogadro's number, and it's really, really useful because of the way that it links to moles. It is the key to linking number of particles with the mass of a substance. Okay. Now we are asked in this question to calculate the number of atoms in 2 moles of neon. So we've got 2 moles of neon, and we're told Avogadro's number here in the question. Now this is only worth 1 mark, so there's not really much that we need to do, but we need to remember what this number tells us. And this number tells us, as we said before, the number of particles in 1 mole of a substance. Now I've used the word particles for a specific reason, which we'll come back to in the other parts of question 4. Okay, so it could be molecules, it could be atoms, it could be a number of things, but it's the number of particles in 1 mole of a substance. So if we've got 2 moles of neon, then that means that we've got twice as many particles as we would have in 1 mole of neon. So we just need to do 2 lots of Avogadro's number. So 2 times 6.02 times 10 to the power of 23. And if we do that calculation, we get an answer of 1.204 times 10 to the power of 24. That is worth 1 mark. 4b then, and we're asked to calculate the number of molecules in 0.4 moles of sulfur dioxide. Okay, so we've got this many moles, we're given the Avogadro number again, but this time rather than atoms, we're being asked for the number of molecules of sulfur dioxide. Now just to remind you, the definition of a molecule, it is when you've got 2 or more atoms covalently bonded together, and that would be in a unit. So for example, sulfur dioxide, which has got 1 atom of sulfur and 2 atoms of oxygen covalently bonded, that's an example of a molecule. So we want to know how many molecules there are if we've got 0.4 moles of sulfur dioxide. Now once again, this is a nice simple question. It is only worth 1 mark. We just take the 0.4, because in 1 mole of sulfur dioxide we will have 6.02 times 10 to the power of 23 molecules of sulfur dioxide. So if we've got 0.4 moles, we just need to do 0.4 lots of that Avogadro's number. So we do 0.4 times 6.02 times 10 to the power of 23, and if we do that, we get an answer of 2.408 multiplied by 10 to the power of 23. That's how many molecules we've got. If you got that right, well done. That is worth 1 mark. 4c then, and you'll notice this one is slightly different. We're being asked to calculate the number of hydrogen atoms in 0.6 moles of water. So we're being asked about atoms in a number of moles of water, which is a simple molecule. So little bit different. So let's see what we need to do here. Well, if we know we've got 0.6 moles of water, using the principles we used before, based on the fact that 6.02 times 10 to the 23 particles in 1 mole, we can deduce that if we do 0.6 multiplied by Avogadro's number, and we do that calculation, we get an answer of 3.612 times 10 to the power of 23 molecules of water. That will get you 1 mark if you manage to deduce that. But now we need to consider about how many hydrogen atoms there are in a water molecule. Now the analogy I like to use here is if you imagine you've got a bike. A bike has 2 wheels. So if you've got 2 bikes, you've got in total 4 wheels. If you've got 10 bikes, you've got 20 wheels. You're always going to have twice as many wheels as the number of bikes you have, because the bike has got 2 wheels. Okay, so if you've got 1 mole of bikes, that means that you'll have 2 moles of wheels. So if you have 1 lot of Avogadro's number of bikes, you'll have 2 lots of Avogadro's number of wheels. So if we look at the formula for water, it has the formula H2O. And if I draw a molecule of water, so a symbolic representation, you'll notice that we've got 1, 2 hydrogen atoms. And it looks a little bit like a bike, doesn't it? Okay, so what we can say is if we've got this many molecules of water, then we'll have twice as many atoms of hydrogen. So we need to do that number times by 2 in order to find out how many atoms of hydrogen we have. If you do that calculation, you get a final answer of 7.224 multiplied by 10 to the power of 23 hydrogen atoms. That will yield you your second mark for this question. Okay? And now we move on to the final one. Part D. The number of hydrogen atoms in 40 grams of methane, which is CH4. So once again, we're being asked about hydrogen atoms. We know we've got CH4, that's our formula, but this time we don't know how many moles of methane we've got. We're told the mass of methane. So we need to be able to figure out the number of moles from the mass. Well, fortunately, in question 3, we've got some experience of doing this already. The moles is equal to the mass divided by the relative atomic mass or the relative formula mass. Now in this case, because we're looking at a molecule, methane, CH4, it is going to be the relative formula mass. So we want to find out what the relative formula mass of methane is. Now we've done this already. The relative atomic mass of carbon, C, is 12. We're told that up there. We've got 4 lots of the hydrogen atom, which has a relative atomic mass of 1. So if we add those values together, we get an answer of 16. If you've got that bit, that will be worth 1 mark. Well done. Now we need to find the number of moles. So we can substitute this number and the mass into our equation. So the moles is equal to the mass, which we've got in the question as being 40 grams, divided by that relative formula mass we just calculated, which is 16. So we do 40 divided by 16, we get an answer of 2.5 moles. And there's your second mark. Now, just before I move on, just a word of advice to you. If in doubt in any chemistry calculation, calculate the number of moles. Okay, do mass divided by relative mass, because there's nearly always going to be that type of calculation in a calculation question. So if in doubt, do that. In this case, it would net you 2 of the 4 marks. Okay, so just a bit of advice. Moving on from there, we've got 2.5 moles. So now we're back where we were in question C. We already knew this information for that question. So if we've got 2.5 moles, we know that whatever that number times Avogadro number is, that will tell us the number of particles in that many moles, okay? Because 1 mole is Avogadro's number of particles. So we're looking at methane molecules. So if we do 2.5 times the Avogadro's number, that will tell us the number of molecules of methane that we have, and if you do that, you get an answer of 1.505 times 10 to the power of 24 methane molecules. But once again, that is not what the question has asked. This will get us the third mark. We're interested in the hydrogen atoms. So, drawing out methane, it's CH4. For every molecule of methane we have 1, 2, 3, 4 hydrogen atoms. So that means that if we had 1 molecule of methane, we'll have 4 hydrogen atoms. If we have 5 molecules of methane, we'll have 5 times 4, which is 20 hydrogen atoms. If we have 10 moles of methane, then we'll have 40 moles of hydrogen. So that means if we've got this many methane molecules, it will be that number times 4 that tells us how many hydrogen atoms we have. So we need to do 4 times 1.505 times 10 to the power of 24, and that gives you your final answer for this question, which is 6.02 times 10 to the power of 24 atoms of hydrogen. So if you got that, well done, all 4 marks. Excellent.